In this lesson, we're going to talk about gambling. It's true, but not to encourage you to do it or to give you any, shortcuts or methods to win. That's not really going to work. We're going to talk about gambling because it's the easiest way to understand expected value. So, expected value is the amount, usually of money, that you can expect to win when you play a certain game of chance. Okay? It has to do with how much you gain by winning and how much you lose by losing, and it connects it to the probability of doing those two things. Okay? So, if you end up with a positive expected value, then it's a good idea to play that game. Then you can expect to come out on top if you play for a long time. So this all hinges on playing a lot. So if you play the game twice, that doesn't really give you a very good idea of expected value. You need to play it a lot because it's how it's going to shake out over time. We noticed in the experimental probability versus theoretical probability lesson that when you flip a coin, you can expect that it's going to be 50-50, that you'll get half heads and half tails, and that will likely start to happen over a long period of time if you flip the coin a lot, like thousands of times. But in 10 trials, there's nothing that says that you can expect to win half the time or to get half heads and half tails. Okay? And so it works the same with a slot machine, let's say. Some people walk up to the slot machine and they think, I've played it so many times, I'm due a winner. Right? I should expect that sometime, in order to balance the probability scales, it's going to let me win yet. But that might not actually be your experience. That's not how they work. Okay? So we have to keep in mind that expected value expects that you're going to play a lot over a lot of trials. Okay? So let's do a few examples here. Consider a simple game in which you roll a 5-sided die and receive $3 if you roll a 5. Okay, so you're rolling a die, you roll it, you get a 5, you get $3. But it costs $1 to roll the die. So it's like a carnival game, right? You pay your money for your chance to play, and then if you win, you get a certain prize back or you get a certain amount of money back. But if you lose, you've just lost that $1 that you paid to play. Same idea here. You pay your $1, you roll the die. If you win, you get $3 back. Okay? But that means you get your $1 back and 2 more. Right? You've only actually made a profit of $2. You haven't made a profit of $3 because you had to pay $1 to play. That's going to be important. So here's our formula for expected value. It's this whole thing. It equals the win probability times the payoff for winning. So in our case, you get $3 for winning, plus the lose probability times the payoff for losing. Okay, let's give this a shot here. So the first outcome is you win. That means you rolled a 5. The other outcome is losing. That's most of the time what it's going to be, winning and losing. I mean, you can split it up into more outcomes than that, but this will work for this one. So this is rolling a 5. This is rolling 1, 2, 3, or 4. So there are 4 losing outcomes and 1 winning outcome. And so that means that your probability of winning is 1 out of 5. Right? So rolling a 5 is a winner, and there are 5 total outcomes. So we're looking at probability, not odds, probability. So your probability of winning is 1 out of 5. And 1 out of 5 is the same thing as 0.2, which is 20%. I can fit it in the box. And then your losing probability, there are 4 losing outcomes out of a total 5. And so that's 4 out of 5, which is 0.8, or 80%. and all of your probabilities should add up to 100. And so we can see that your winning probability being 20% and your losing 80% will add up to 100. Okay? And so the amount you win, if you win $3. If you lose, you don't win anything. And so it's 0. Okay? Yes, I remember that you had to pay $1 to play, but that is going to come into play later. Okay? So when you are calculating your payoff, that is when you take into account how much you had to pay to play. So we're going to take the amount that you won. You won $3, but you had to pay $1 to play, and so your payoff is $2. Okay, so the payoff for winning is actually only $2 because it cost you $1 to play. And then your payoff for losing, you won nothing, and you had to pay $1, and so your payoff for losing is negative $1. And so now we're going to do the last part. So we've done this win probability. We figured out the win probability. We figured out the payoff. We figured out the lose probability. We figured out the payoff for losing. And now we're going to put it all together. That's what the last box is for. Okay? So our last box goes like this. We can either go 1 over 5 times 2, because we're doing the probability times the payoff, or you can do it as a decimal. Some of your calculators are probably going to be easier than others to put fractions in there, and so you can feel free to do that, but I'm going to write in the decimal because everybody's calculator will be able to do that easily. So 0.2 is the probability of winning. We're going to multiply that by the payoff, which is $2. 0.2 times $2 is 0.4. That's what your calculator will say, but you need to know what that means. What is 0.4? We're talking about money here, right? So this is $0.4 or 40 cents. Okay? Hopefully that makes sense. Usually we write money out this way with dollars, decimal, cents. So when your calculator tells you 0.4, it really means 40 cents or $0.40. The probability times the payoff for losing is 0.8 times negative $1. And that gives you negative 0.8. That's what your calculator will say. And again, you'll tell yourself that means 80 cents or $0.8. But that's negative. So you can expect that you're going to lose 80 cents and gain 40 cents on average if you do this lots and lots of times. And so in total, when you add these two things up, you get 0.4 minus 0.8. So 0.4 minus 0.8 equals negative 0.4. Your calculator can tell you that. But again, we're talking about money here. And so this is negative 40 cents. And so here's what expected value means. If you were to play this game a large number of times, you could expect to average losing 40 cents per round. Okay? And so if you play this a lot of times in order to make that expected value make sense, you're going to lose a lot of money. Okay? So this game is not a good game to play. Everybody kind of thinks, but there's a chance. There's a chance that I'll win. Right? That's the idea behind sweepstakes and lotteries, that although there's a very tiny chance that you're going to win, somebody's got to. Maybe it's going to be me. And so we get this kind of inflated idea of our chances of winning. And expected value kind of brings that back down to earth. Okay? And so for this simple game, you can expect to average a loss of 40 cents per round if you play for a long time. Again, that's if you play for a long time. If you play twice, you might win both times. You might win $4 then, right? Because you had to pay $2. So you might win $4 if you only play twice, but if you play a lot, you can expect that you're going to lose 40 cents in total. If you played this game 100 times, how much would you expect to win or lose? So we just said that you can expect to lose 40 cents every single round. That's the average. And if you played this 100 times, yes, you're going to win some of those times, but you're going to lose more of those times, likely. And so we do 100 times negative 0.4, or negative 40 cents. 100 times 40 cents is $40. You can expect to lose $40. So a $40 loss. Not a great game to play. So expected value tells you, is this a smart game to play or not a smart game to play? Frankly, there is really not a gambling game that's a smart game to play if you're going to play it a lot. You're just kind of banking on getting lucky once. Let's try the second example. What is the expected value of the following game? It costs $1 to roll a 6-sided die. This is a regular die now, not the 5-sided thing we were talking about. And if you roll an even number, you receive $3 back. So it's the same cost and the same payoff, but the outcomes have changed. Okay, so before we had 1 outcome out of 5 that was a winner and 4 outcomes that were losers. In this case, all we need to do is roll an even number. So in a 6-sided die, you've got 1, 2, 3, 4, 5, and 6 are your outcomes. So the winners would be 2, 4, and 6. So 3 out of 6 of the outcomes are winners in this case, or half of them, if you want to bring it down to lowest terms. And so we can figure out the expected value of this game using our formula. Okay, so we can use a table again if you like to organize things that way. So the winning outcomes and losing outcomes. The winners are 2, 4, and 6. The losers are 1, 3, 5. And so the probability is going to be 3 out of 6. 3 out of 6 probability for winning, 3 out of 6 probability for losing. Same probability. In gambling, that's never the case. You'd never have the same chance of winning and losing. But let's just go with it. So if we make this a decimal, because we're going to use a decimal later, that's 0.5. You just do 3 divided by 6. Same thing with the bottom one. 0.5. Okay, so how much do you win? How much money do you win? That's the question. Let me put. So you win $3 if you win, and you win $0 if you lose. I don't know very many games where you win something if you lose. The payoff. So you had to pay $1 to play, and so you have $2 left if you win, right? Because you won $3, but you had to pay $1, and so your payoff is $2. The payoff for losing, you won $0, and you had to pay $1 to play, and so just like before, your payoff is negative $1. Okay, now the last piece that we need to do, this is all just organizing your information really. The actual calculation is this last part. It's the probability of winning times the payoff for winning plus the probability of losing times the payoff for losing. So let's do this calculation. It's the win probability times the payoff plus the lose probability times the payoff. So the win probability is 0.5 times the payoff, which is $2. 0.5 times $2 is positive $1. And then the lose probability is 0.5 times the lose payoff is negative $1. 0.5 times negative $1 is 50 cents. Negative 50 cents. 0.50. And so then we need to add these things up to get the total expected value. So positive $1 plus negative 50 cents, or $1 minus 50 cents, that's the same thing, is positive 50 cents. We put the dollar sign in there. So I can expect that if I play this game a lot, that on average I will win 50 cents per round. That is a good game to play. Again, that's never going to happen while you're gambling, but if you could, it's perfect. So if you played the game 50 times, how much would you expect to win or lose? So then we do the total number of times that we're playing, and I'm playing it 50 times, and every time I'm averaging 50 cents. So 50 times 50 cents each equals $25. And that's positive $25, and so I should expect to gain that much. So $25 gained. Let's make it gained. Okay, that's a great game to play. If the cost instead was $2 per roll instead of $1 per roll, then what happens? So let's not redo this whole thing. What changes? So the payoff is going to change, right? You still win $3 or you lose and don't win anything. And so the payoff changes like this. Now for winning, it'll be 3 minus 2. So now you only win $1. And the payoff for losing is 0 minus 2. And so you lose $2. So that's negative $2. Okay, and then we'll redo the final calculation, right? So the probability is still the same. It's still 0.5 times, now our payoff is only $1. And that equals 50 cents. And our payoff for losing, 0.5 times negative $2, you can already see it's going to be more, right? And so now that's $1 or negative $1. We're losing $1. And so then when we do this calculation here, our expected value just flips. It used to be positive 50 cents, and now it's negative 50 cents. So the cost now, the cost of playing has turned this from a good game to play, one where you can expect to actually win over the long term, into a bad game to play, where you can expect to lose over the long term. And here's the last piece. This is the only example that doesn't involve gambling in some way. Based on past experience, a business person determines the probability of receiving a computer contract is 0.2, or 20%, or 1 out of 5. Those are all the same. The contract is worth $12,000, and the person determines that it would cost $1,500 to prepare a contract proposal. Determine the expected value for this situation. So if someday you run your own business, or your parents run their own business right now, maybe you are aware that it costs something to prepare an estimate for somebody. So let's say that somebody wants a renovation done to their home, and your parents run a construction company. They actually have to go there, spend their own time looking around, taking measurements, that kind of thing, to figure out what is a reasonable amount of money to bid for the job. How much is it going to cost them? How much time is it going to cost so that they have to pay their employees that much? And so it costs something. It costs time to even do the estimate. Okay, and so in this case, we're looking at the same thing. This person has to prepare a proposal in order to even bid for this contract. And they only have a 20% chance of actually getting the contract based on past experience if they do prepare that proposal. So we're going to figure out how much can this person expect on average, if they did this a whole bunch of times, how much can they expect to earn? Is it worthwhile to prepare the contract, or is it really not worthwhile to even throw your hat in? Okay, so either they're going to get the job or not. So they're going to win the contract, or they are not going to win the contract. They're going to lose the contract. And the probability of winning the contract is 0.2. And the probability of losing the contract then is 0.8. Okay, so if that wasn't straightforward, think of 0.2 as 20%, right? So we multiply it by 100 to get the percentage. And so that's 20%. And so if winning is 20%, how much is left out of 100? 80% is left. And so 80% is the other piece. But as a decimal, that's 0.8 because you divide it by 100 to change it back to a decimal. Okay, so we've got 20%, where 0.2 is the chance of winning, 80% is the chance of losing. The amount that you win is $12,000 for getting the contract and nothing for not getting the contract. Then we have to figure out what's the payoff. I'm going to label that because that is an important piece. Payoff. So the payoff for this job is how much you win minus how much it cost you. Okay, and so you win, for lack of a better word, you get paid $12,000, but you had to spend $1,500 to prepare the proposal. And the payoff for losing would be 0 minus 1,500. So if you prepare the proposal and then don't get the contract, then you didn't make any money, 0, and you spent $1,500. And so then our calculation is the last piece. We're doing probability times payoff, probability times payoff, and adding them up. So the probability of winning is 0.2. And the payoff for winning, should probably do that calculation, hey? It's $10,500. So that's the payoff for winning. Payoff for losing is negative 1,500. Okay, I'm going to just separate this here so we know the different pieces. So this is the win probability times the payoff, which is $10,500. And the lose probability is 0.8. And you're going to lose $1,500. Now we're going to multiply these things out, figure out how much can I expect to win on average, how much can I expect to lose on average. And so when you do that, you get $2,100 is your expected profit, and your expected loss, 0.8 times 1,500, is negative $1,200. And our total expected value is just adding those two things up, or in this case, subtracting them. I mean, it's really always subtracting them. So 2,100 minus 1,200 is plus $900. Remember, that means that on average, you can expect that if you would do this thing over and over and over again for a lot of times, you would end up averaging $900 of profit per contract. So you're still going to lose a lot of them, but you're going to win some of them, and so then you would end up with a $900 profit. So it's a worthwhile thing to do. If a person bid on 30 such contracts, on average, what would the gain or loss be? We always have to talk about on average because you never know in a particular case. So we're doing 30 times your expected win or loss, which is $900 in total, and 30 times $900 is $27,000. So if you took 30 contracts at an expected value of $900 per contract, you could expect to make a total of $27,000 of profit on average if you did that 30 times.